Always ends the same when it was me and you. But every time I meet somebody new, it's like deja vu. I swear they sound the same. It's like they know my skin. Every word they say sounds just like him. And it goes like this. We get in your car and you need to kiss me. We'll talk for hours and lie on the backseat. And then one random night when everything changes, you won't reply and we'll go back to strangers. It's something that I hate, how everyone's disposable. Every time I date somebody new, I feel vulnerable.
Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So in this video, we're going to learn about the Prim's algorithm, which will help us to find the minimum spanning tree. What is the minimum spanning tree? I've already discussed in the previous video. So you can just go back in this particular graph series in the previous video, understand what is the minimum spanning tree, come back and start with the Prim's algorithm. So Prim's algorithm is an algorithm which helps you to find this particular MST. Now, imagine this is the graph given to you. So what will be the MST of this particular graph? Very simple. If you remember from the previous lecture, 0, 1, we have a 2, we have a 3 here, and we have a 4 here. So if you connect these guys, and if you connect these guys, it'll be 6, 2, 5, 3. And if you sum them up, you will get 6 plus 2, 8 plus 3, 11 plus 5, 16. So 16 is what the summation is. So Prim's algorithm does help you to find this particular summation, which is nothing but the MST's weight. We can usually call this as MST's weight, or even if you want the edges, like for example, the edges involved in the tree are 0, 1, 0, 3, 1, 4, and 1, 2. These are the n minus 1 or 4 edges which are involved in MST. So you can also get this particular thing if you are looking for. So Prim's algorithm does help you to find the sum as well as the particular tree, which is indeed the MST. So in order to understand Prim's algorithm, we will be using this particular graph. So before starting Prim's algorithm, we will be requiring a couple of initial things. One is a priority queue is what I'll require. Why I'll tell you while I explain the algorithm. And the other one is a visited array, which I'll be requiring. Again, I'll be telling you why will I be requiring a visited array while I explain this particular algorithm. So the initial configuration will have a priority queue or a minimum heap in which I'll be storing the weight, the node, and the parent. Along with that, I'll have a visited array, which will be initially marked with unvisited with all the nodes. And we will have a sum of 0, which will count the MST's edge weight. And I'll have an MST list, which will be storing all the edge which are. Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So in this video, we're going to learn about minimum spanning tree, which is more commonly known as MST. So in order to understand minimum spanning tree, the first thing that you need to understand is what is a spanning tree. So you will be given an undirected weighted graph. So the edge will have different or equal weights, and this graph will contain n nodes and m edges, where n can be any number, m can be any number. There is no relation between them. So if you see as of now, this graph is connected by 1, 2, 3, 4, 5, 6 edges, correct? And how many nodes are there? 1, 2, 3, 4, 5. So this graph is currently having 5 nodes and 6 edges. Now the task of a spanning tree, or the definition of a spanning tree, is, write the definition, a tree in which we have n nodes, very, very important. We have n nodes and n minus 1 edges. That is the definition of spanning tree. A tree in which we have n nodes or n minus 1 edges, and all nodes are reachable from each other. And all nodes are reachable from each other. So if someone does ask you, So Prim's algorithm is an algorithm which helps you to find this particular MST. Now, imagine this is the graph given to you. So what will be the MST of this particular graph? Very simple if you remember from the previous lecture. Yeah, and if you sum them what? It, or even if you want the edges, if for example the edges involved in the tree are 0, 1, 0, 3, 1, 4, and 1, 2. These are the n minus 1 or 4 edges which are involved in MST. So you can also get this particular thing if you are looking for. So Prim's algorithm does help you to find the sum as well as the particular tree, which is indeed the MST. So in order to understand Prim's algorithm, we will be using this particular graph. So before starting Prim's algorithm, we will be requiring a couple of initial things. One is a priority queue is what I'll require. Why I'll tell you, I'll explain the algorithm. And the other one is a visited array, which I'll be requiring. Again, I'll be telling you. Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So in this video, so in order to understand Prim's algorithm, we will be using this particular graph. So before starting Prim's algorithm, we will be requiring a couple of initial things. One is a priority queue is what I'll require. Why I'll tell you, I'll explain the algorithm. And the other one is a visited array, which I'll be requiring. Again, I'll be telling you why will I be requiring a visited array while I explain this particular algorithm. So the initial configuration will have a priority queue or a minimum heap in which I'll be storing the weight, the node, and the parent. Along with that, I'll have a visit which I'll be explaining the weight particular algorithm. So the initial configuration will have a priority queue or a minimum heap in which I'll be storing the weight, the node, and the parent. Along with that, I'll have a visited array, which will be initially marked with unvisited with all the nodes. And we will have a sum of 0, which will count the MST's edge weight. And I'll have an MST list, which will be storing all the edge which are part of the MST. So initially, remember, you will start off with any given node. It can be any given node that is your choice. So what I'll do is I'll start off with something like 0 with the weight, 0 with the node, and I can say the parent is -1. Remember this. This is what I will initially insert: 0, weight, 0 node, -1 as the parent. Okay, now we will start the iteration. Remember, no visited mark. We just put it into the priority queue. That is the initial configuration. Now we start the iteration. So while we start the iteration, we get only element on the priority queue, which is at the top, which is 0, 0, -1. So this is the node, this is the parent. So whenever the parent is -1, it means it's not an edge. It's the first node. Parent -1 means it's the first node. So do not add it into the MST. Do not add it into the MST. Also, there is no edge weight because this is the first node. That's why there is no edge weight as well. So we have the first node as 0. Make sure you go across and mark it as visited. Marked it as visited. Now, stand at 0 and look at the adjacent nodes. So when you stand at 0, you look at one of the adjacent node is 1, and that's still unvisited. So what you do is you take 1 and you say the edge weight is 2. So 2, 1 comes from 0. So basically you were standing at 0. So you took the edge weight 2, you took the node 1, and it came from 0. So basically this is the edge that you took. Perfect. Done. Next, this is also connected to 0. So what you'll do is you will see, is this unvisited? Yes. So simply take 1 as the edge weight. So I'll take 1 as the edge weight. The node is 2, came from 0. So what I did was I take both the guys who are directly connected to 0, but please do not mark them as visited. Please do not mark them as visited. Okay. So I've taken it. So I can say the first iteration has been complete and I have pushed on all the adjacent nodes into the minimum heap data structure. Now, what does minimum heap data structure say? We will always have the least weight at the top. So I'll get the least weight guy, which is 1, 2, 0. So 1, 2, 0. This time you're getting an edge 0, 2. You're getting an edge 0, 2. So it will be a part of your MST. 0, 2 is a part of your MST, and whatever is the edge weight, you'll go and add it on the sum. Done. Now you have edge as you have the node as 2. So go to the 2 and say you are visited, right? Next. So you have taken 0, 2, and that is what you have taken. Now stand at 2. So you stand at 2 and you look at 0, but 0 is already visited. So do not look at 0. You look at 1. 1 is unvisited. Yes, 1 is unvisited. If you stand at 2 and look at 1, it's still unvisited. So it's an edge weight of 1. So you can again take 1, and this time you came from 2, and this time you came from 2. You can easily take it off. Okay, next. If you're standing at 2, 0 is done, 1 is done. Next adjacent is 4. It's unvisited, so you can again take it. So 2, 2 is the edge weight, 4 is the node, and you're coming from 2. So this is what you'll put it into the priority queue. Do I have anyone else? We have a 3. Yes, we have a 3. So what I'll do is I will this time take the edge weight 2. We will take 3, came from 2. Perfect. So apparently this is also done, and I made sure standing at 2, all the adjacent guys have been put into the priority queue. Next, take the next smaller guy, out of which is the next smaller guy? Obviously 1, 1, 2. So take 1, 1, 2. So 1, node 1, parent 2. Go and look at the node 1. Is it unvisited? It is unvisited, which is 1, 2, which is nothing but this edge. So I can say I'll take this edge now. 1, 2 is the edge, or rather 2, 1. You can call it whatever, because 1, 2 or 2, 1, both are same, right? And the edge weight is 2. So the edge weight is 1, so you add 1 to it, I'll get it as 2. And at the same time, make sure you mark it as visited. Separately, now 1 is also visited. Now stand at 1 and look at its adjacent. Its adjacent is 0, which is visited. Its adjacent is 2, which is visited. So there are no other adjacent. So thereby, I can say the iteration has been completed. Now let's look at the next one. What is the next one? Which I'll get. All of them are same. Separately, we will get this guy. So 2, 1, 0. 2, 1, 0. But before moving ahead and adding this to your sum or to the MST, we see, hey, wait, the node 1 is already visited. So you do not add it. Yes, you do not add it. And you do not do any adjacent operations. If the one has already been visited, which means it's a part of your MST. It's a part of your MST. So do not add it, right? Next, you find out the next guy. So out of these two guys, we'll take 2, 3, 2. So 2, 3, 2. This time, which is the node 3. So go and mark 3 as visited. Next, this is the edge weight. Go and add it. So this will be 4. Next, this is the edge 2, 3. Go and add it to your MST. Now you're standing at 3. Stand at 3. Look at its adjacent. One of the adjacent is 4 with 1. So well, you can add it. 1, 4, 3. I've added it. And for 3, the other adjacent is 2. So 2, 2, came from 3. We've added that into the priority queue because for this guy, this was one of the adjacent and this was one of the adjacent. So I've added both of them. I can say my iteration has been completed. Now, quickly, which one is the smaller? 1, 4, 3. So take it out. 1, 4, 3. Is 4 unvisited? What you'll do is, get done. And so what I'll do is, I'll quickly erase this off and try to draw the MST so that the idea is clear to you. Let's see. 2. This is how you do it. So I hope the algorithm is clear to you. Very simple. Take the elements out. If it's unvisited, mark them as visited. Take the adjacent nodes, put them into the priority queue. Keep on going. And ultimately, you will get your MST. So I hope you've understood the entire explanation. Now it's time to code it up. So as usual, I'll be coding the C++.
Hello everyone. Today we'll talk about another algorithm to find the minimum spanning tree. It's called prim algorithm. And again, we'll use A to store all the edges of the minimum spanning tree. So initially A is empty and eventually we'll return A. And then for each vertex in the graph, we give it two attributes, a key and a parent. Each key is initialized to infinity and each parent is initialized to null. So this is the initial condition for all the vertices. And then we randomly choose a root and set the key of that root to be 0. So we pick A as the root and set A's key value to be 0. Then we create a queue which contains all the vertices in the graph. Next, we enter the while loop. We find the vertex in queue with the smallest key. In this case, the vertex in queue with smallest key is A because A's key is 0. Then we remove A from queue. Since the parent of A is null, so we'll skip this statement. Then we'll update the attributes for all the vertices who is adjacent to A. Let's start with F. If the weight of the edge is less than the key of F, we'll update F's key to be A. Let's start with F. If the weight of the edge is less than the key of F, we'll update F's key to be this weight and F's parent to be A. Same thing for B. Since the weight of the edge is less than the key of B, we'll update B's key to be the weight and B's parent to be A. Now enter the second loop. A has been removed from Q, so now Q contains all the vertices in purple. The vertex in Q with the smallest key is F, since F's key is 2. And the parent of F is not null, so we need to execute this statement. We'll push the edge between F and F's parent, in this case, this edge, into A. So this is one of the edge in minimum spanning tree. of the A. So in this case, all three will be updated. And both A and F has been removed from Q. Now enter the third loop. The vertex in Q with the smallest key is C. So we remove C from Q and add the edge of CF into the minimum.
In this video, let's learn about Prim's algorithm. Prim's algorithm is a greedy method to find the minimum span. If you take here, if you pick A and C, they should be connected just with one well-defined path that we are constructing. Now to see it here, we have it going to express this path in the beginning. We can easily construct the spanning tree. So R as the input. How are we going to express this spanning tree as a result? We can simply have an array, a parent array, which could tell us what is the parent for each of the vertex. See here in this spanning tree that we have constructed, if you take the vertex 1, 0 is the parent of 1. Similarly, 0 is the parent of 3 and 0 is the parent of 4 as well. So if we have such information in an array and also this adjacency matrix, we can easily construct this spanning tree. So our code should be able to give us a result like this. We are going to start with some vertex and then we are going to add more vertices to our spanning tree, right? So we obviously need some kind of Boolean array which could tell us what are all the vertices that have already been added to the spanning have an element. So we are 0 to the so in O to the of this we all third word now connections. So we can update a 3 here in the parent
Hello guys, welcome back to TechDose. Compute all that to value 2.
In our graph theory, we are having mainly two algorithms to find out the minimum spanning tree from a given graph. These two algorithms are Prim's algorithm and Kruskal's algorithm. Now, in case of Prim's algorithm, it requires one seed vertex from where this minimum spanning tree will be formed. We know that in case of minimum spanning tree, we shall connect all the nodes, all the vertices of a given graph, and here obviously initially the graph will be the weighted one, and then in that case the tree thus formed will have total weighted sum minimum, and thus it is called minimum spanning tree. That means all nodes will get connected through that tree and the total weighted sum will be minimum for that solution. Obviously, the minimum spanning tree might not be unique. There might be another parallel solution, and in that case, obviously, it is Prim's algorithm and Kruskal's algorithm. They are not taking the responsibility that they are going to give you the unique solution. Okay, now let us go for the algorithm at first. How does it work? See. So function prim, it is taking a graph G as input argument, and this graph G is consists of set of nodes and set of edges. Set of nodes have got denoted by capital N, and set of edges or arcs are denoted by capital A, and that is the graph. And it returns the set of edges, and that is the output argument. It is showing that it returns the set of edges. What are the edges? Edges of the minimum spanning tree. Initialization, t is equal to phi. So that means t is a set which will be initialized with phi. That means just curly brace open, curly brace close. So I'm just initializing t with the phi. And then b, an arbitrary member of n. I told you this one earlier that Prim's algorithm requires one seed value, the seed vertex from where this minimum spanning tree will grow. While b is not equal to n, this algorithm is falling in the category greedy algorithm category. So now what will happen in the next sessions, in the next part of the algorithm, we can find that b will go on increasing. That means accumulating other data. That means accumulating other vertices. So now b will go on enriching itself. So until b is not equal to n, that means until all the vertices have got considered, and that means the same thing. That is, a b is containing, until b is containing all the vertices. That means when or while b is not equal to n, do find E. What is E? E is the edge which is connecting two vertices U and V. So U and V of minimum length such that U belongs to B. What is B? Set of considered vertices. So U is considered already, but V is not considered. So V belongs to N minus B. What is N? Set of all vertices. What is B? Set of all considered vertices. What is N minus B? Set of all unconsidered vertices up to this level. So now that is UV. So U must be belonging to this set and V must be belonging to this set. Okay, done. So now find E. So find such edge of minimum length satisfying these two, and if you get such, then please go on union, that is T union E. So E will be union with T. So I think it is better, without putting it within fast brackets, it is better to put them in this curly braces. Okay, so T is equal to T union E and B is equal to B union B. That is, the V was unconsidered vertex, now it is getting enriched or getting accumulated in B. So B B is the size of B is now increasing. So after some times, after some iterations, B will be equal to
press on the right, and percent is 4 with 1. So now what I'll do is I'll quickly erase this off T. So I hope you've understood the entire explanation. Now it's time to code it up. So as usual, I'll be coding the C++ on the right, and you can find the exact similar Java solution on the left. So what does the question state? Given a weighted, undirected, connected graph of vertices and edges, task is to find the sum of weights of the edges. They don't want you to find the minimum spanning tree. They want just the sum of the weights of the edges. So what I'll do is I've been given the V and the graph. So I'll declare a priority queue at the first because that is what I require. So this is how the priority queue will be, or the minimum heap. And what else do we require? We require a visited guy. So let's take a visited guy if you remember, and I'll mark everything as 0. And in the priority queue, initially, now over here, one thing I'd like to clarify, we just need the sum of weights of the edges. So do we need to carry the parent? No, because what we needed was the weight, so that in priority queue you always get the minimal weight. And the other thing that I always needed was the node. I needed the I would have needed the parent if some someone would have told me to get the MST. But over here, the question is just the sum of weights of this. So I'll just store something like the weight, comma the node. That's it. No need to store the parent. If they ask you for MST, you can go ahead and store the parent. Okay. But over here, we don't need anything. So what I'll be like, okay, while pq dot empty, that's the case. So what I'll get is auto of id as pq dot top. Okay. And at the same time, I can do pq dot pop. Now I can say the node will be at the second position. So I'll get the node, and I know one thing: the weight will be at the first position. Now something I know for sure is if this node is already visited, that means it's already a part of the MST. So I'll say, hey, no need to do anything. If it's already the part of the MST, or I can say that's rather this. If it's already visited, just go ahead. Just go and get the next node. If it's not visited, I'll say, okay, come ahead, be a part of the MST. Come ahead and give it to the sum. So probably I can declare something like sum equal to 0. That's what I'll do. It'll be a part of the MST. In case someone would have asked you to get the MST, you would have taken the parent and stored it in some list in this position. Okay, but we don't need it. Now what's the next thing? We've got the node. Get all the adjacent guys. Yes. How do you get all the adjacent guys? Very simple. Iterate on all the adjacent guys like this. And then who is the adjacent node? This guy. Yes. And what's the edge weight of that guy? This one. Right. Now what do you need? If it's not visited or not a part of MST yet, if it's not a part of the MST yet, then I go ahead and say, okay, you're not a part of the MST. Can you go ahead and get into the priority queue? Simple. No need to mark it as visited. We mark it as visited on ahead and say, okay, you're not a part of the MST. Can you go ahead and get into the priority queue? Simple. No need to mark it as visited. This So very simple. And once you've done this, you need to return the sum. So go ahead and return. Let's quickly submit this and see if it is running all the test cases.
Hi and welcome to Geeks for Geeks. Priority test of all, just like here, the highest element is 80 and it is printed.
Hello everyone. So in this video we're going to see about priority queue in C++ STL. So let's get started. So first let us discuss about the functionality of a priority queue. Okay. So the priority queue works based on heaps. So there are two types of heaps, min heap and a max heap. Parent element as well, but so it's larger priority queue. And for pushing values inside priority queue is going to be q dot push. That's it. So let me just put 10 q dot push 0 just q dot balance in that. So if I just save and run it now, I'll be getting 20 in the output because by default this normal priority queue will be a max heap. Okay, so it will have the functions of max heap. So I'm getting 20, and there is also like another function q dot size as well. Same thing. If we just run it, I'll be getting the size as 4. 4 I'm getting 4. Now let's delete an element. Okay, so same thing for deleting it. It is q dot pop. So as I told you in the example, it will delete the largest element from the set of values. So in our case, our largest element is 20. So 20 will be now removed completely. And after removing 20, if you put cout q dot top, it will go on to the second largest element, which is 10. Okay, so as I told you, consider which 10 now as well. Just now remove this. So 10 will be going over there. So if I put q dot top, I'll be getting 10 now as output. So I'm getting 10 as output. I hope that made sense. And let's go for a min heap or a minimum priority queue. Okay, so for that, what you do is you just put a comma and you add vector int and comma greater int. Okay, so usually we will only add greater int. We won't be adding vector int. So in this case, we need to add vector int as well. So now let me just comment this one. So now if I just would do q dot top, I'll be getting minus 1 as output because as you know, it's going to be like min heap. So minimum value will be getting popped. So I'm getting minus 1 in the output. And if I just now remove this, I'm doing q dot pop and then q dot top. So what happens is that q dot pop. Okay, so minus 1 will be removed, and next to the smallest element is 0. So same thing, we are removing 10 over. So last
we see all the. Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So today we will be learning about the Kruskal's algorithm. But wait, before starting this video, please go back and watch my video on disjoint set. It's a bit long video, but you'll get a lot of clarity about the concept. Hey everyone, welcome back to the channel. I hope you guys are doing extremely well. So in this video, we're going to learn about the most important topic in the graph series, which is the disjoint set data structure. It's a very, very important topic. Why? This is commonly asked in almost all interviews and the online assessments as well. So you need to master this topic. And in order to master this topic, you have to watch this video and all the follow-up problems that I'll be solving in the next part of this graph series. So let's understand why is disjoint set data structure used. So imagine I give you something like 1, 2, 3, 4, and I give you other portion like 5, 6, 7. This is a single graph, but it has two components. First one is this, second one is this. Now suddenly someone will come up and say, hey, does 1 and 5 belong to the same component or not? How will you determine? You'll pick up 1 and you'll start a DFS traversal. 1, 2, 3, 4. And the traversal is complete. You could not find 5. Since you could not find 5 in the DFS traversal of 1 in that component, you'll be like, they do not belong to the same component. You did a DFS traversal and that's the brute force. How much time will the DFS traversal take? N plus E. That's the complexity the DFS or the BFS takes. Already discussed this in the previous section of the graph series. If you do not know DFS or BFS, go back and watch it. So the brute force is going to take a kind of linear time complexity. So this is where something like disjoint set comes in and says, hey, I'm going to do the same thing in constant time. You ask me, does 1 and 5 belong to the same component? I'm going to tell you in constant time, either a yes or a no. That's the use case of disjoint set data structure. And one more thing, it is usually used in dynamic graphs, graphs which keep on changing, graphs which keep on changing their configuration at every moment. What do you mean by exactly changing configuration? I'll explain you that in the later part. So disjoint set gives us two options. One is finding the parent. That's one of its main functionality. And the other main functionality is union. Now this union can be done with two methods. One is rank, other one is size. I'll be discussing both of them. But so primarily it gives you two functions, find parent and union. Now I did talk about dynamic graphs, graph changing configurations. So let's understand this. Now what do you mean by these things? These are all edges. There's an edge between 5 and 6. Okay. So initially what we assume is 1, 2, 3, 4, 5, 6, 7. Everyone is alone. So initially, before all these edges formation, every node is single, right? So you have 1, 2. What it means is I'm asking you to connect 1, 2. So that is what union does for you. Remember this. Whenever I say connect 1, 2, union in disjoint set will do it for you. We'll talk about union in details, but as of now, know the higher level of union. Union will go and connect. So what I'll do is I'll go and connect. Okay, done. Next 2 and 3. Connect 1. Next 4 and 5. Connect 4 and 5. Next 6 and 7. Connect 6 and 7. So you see the graph is changing at every instant. But you'll be like, but Striver, wait, this is how graph is formed. But what happens here is if I stop the formation over here and I give you a question where after this formation, I suddenly ask you, hey, does 4 and 1 belong to the same component or not? You will say no. Why? Because 4 as of now is here. 1 as of now is here. Till this point, they are not in the same component. So the answer will be no. So in any stage, someone might come up and ask you because the graph is changing at every step. But I can ask you a question at any step and you should be able to answer that in constant time. That is what disjoint set will do. And I'll explain you how it does. Next, 5 and 6. Let's connect 5 and 6. Next, 3 and 7. Let's connect 3 and 7. Now if I ask you the same question, does 1 and 4 belong to, like after performing all the operation, does 1 and 4 belong to the same component? Your answer to that will be yes, they do belong to the same component. Understood? So you saw till here the graph was something different. The moment you performed the next two operations, the graph was a combined one. So I can ask you this particular question, or any U and V belong to the same component at any particular time. So this is the use case of disjoint set data structure. Now let's quickly check out what is find parent and what is union exactly. So in order to implement disjoint set data structure, we can implement union in two ways. One is the rank, the other one is the size. So I can follow two ways of doing it. Okay. But initially I'll be teaching you the rank. I'll be coding you up, showing you how to write a clean code so that it can be reused in almost all the problems. And then I'll be teaching you the size one. So the video will be like first union by rank, then union by size. Okay. So let's understand rank. So in order to implement union by rank, we will be requiring a couple of arrays. One is the rank array, while the other one is the parent array, which will serve for finding parent. I'll explain you. So let's quickly assign the rank and the parent arrays. Okay, so the initial configuration is very, very simple. What we do is we assign a rank array with the same size of the number of nodes. Since the graph is 1 based indexing, I start the array from 1. So everyone is assigned to 0. Okay, so what does rank 0 mean? So if you see this particular node, there is no one beneath it. So it means there is no one beneath it, 0 nodes beneath it. But eventually with the optimizations that we will do, the meaning will change. So I'll explain you throughout the course. So now we have a parent array. Now remember, initially everyone is the parent of himself. Now what does parent mean? Parent. Okay, right above guy. That is what is the definition of the parent, which is stored here. Again, over the course of this lecture, the definition of parent will change as we do multiple optimizations in order to obtain a constant time complexity. So this is what we currently have. Let's quickly start the operations. So let's quickly write the pseudocode for the union of u comma v. So remember, the step one is very, very simple. The step one says find ultimate parent. Yes, find ultimate parent of u and v. What is the meaning of ultimate parent? I'll explain you. And we can term this as ultimate parent, like ultimate parent of u and v. Let's term this as pu and pv. Pu means ultimate parent of u, pv means ultimate parent of pv. Now find rank of those ultimate parents. Find rank of pu, pv. Find rank of ultimate parents, not u and v, ultimate parents. Okay. Now connect smaller rank to larger rank. Connect smaller rank to larger rank always. In case of equality, you can connect anyone to anyone. We will explain that as we move. Okay, cool. We have understood, or I've written the pseudocode. Okay, let's now quickly check out the first operation that has been asked for us. It says union of 1, 2. So what I do is I have 1. So I go and look at the parent of 1. What is the ultimate parent? You have a bunch of nodes. The guy at the top is known as the ultimate parent. Okay, so for 1, who is the ultimate parent? 1 itself. For 2, 2 is the ultimate parent. So I can say, as of now, the ultimate parent of 1 is 1 and the ultimate parent of 2 is 2. What is the rank of both? Can I say the rank of both is as of now 0? If you carefully see, both the ranks are 0. So if they are equal rank, you can actually connect anyone to anyone. Very, very important. You can go ahead and connect. Either you can connect like 1 here, or either you can connect 2. It is completely your choice. So what you do is, you will go ahead and take this 2 and say, can you please connect with, or I can change the color. Can you please connect with 2? And you'll go to that. Now your above parent is 1. Now remember, you connected 2 to 1, right? Both of them had same level. Both of them were equal height. You took it and connected. So the height increased. And if the height increased, the rank will also increase by 1. The rank will also increase by 1. Done? Perfect. Next, 2, 3. And this is where again the next thing comes. Who is the ultimate parent of 2? Let's see who's the ultimate parent of 2. It's 1 over here. And is the 1 the top guy? It is. So the ultimate parent of 2 is 1. Who is the ultimate parent of 3? 3 itself. What's the rank? Rank of this particular 1 is 1. Rank of this particular 3 is 3. If you see 1 is 1, 3 is 0. Sorry, it will be 0. Who is the greater guy? This one. So 3 will come up and get connected. The smaller guy comes up and gets connected to the larger one. So 3 is connected to this. Now I'll go and erase this. Connected. Do I do anything to the ranks? No, you will not do anything to the ranks. Why? Because it still has a height of 1. Because you connected a smaller to the larger. So the larger is not going to increase. It's not going to increase. So thereby we keep the same height. Perfect. Next, connect 4 and 5. Who is the ultimate parent of 4? 4. Who is the ultimate parent of 5? 5. What's the rank? 0, 0. Connect anyone to anyone. So what I'll do is I'll go ahead and connect 5 to 4 and I'll erase this. I'll update the parent of 5 to 4. And the other thing that, by the way, I forgot to update the parent of 3. It will be 1. So what the other thing I'll do is I'll increase the rank by 1 because Two same guys connected. Update the parent. Next, connect 4 and 5. Who is the ultimate parent of 4? 4. Who is the ultimate parent of 5? 5. What's the rank? 0, 0. Connect anyone to anyone. It will be 0. It will update. Connect 5, 2, 1. This is how you can easily connect them. Perfect. Done. So apparently I can just remove this as well. So as of now, this is where we stand. What's the next thing? It says connect 5 and 6. So perfect. So who is the ultimate parent of 5? Let's see. Ultimate parent of 5. 5 is here. So 5's parent is 4. Who is actually the top boss? Who is actually the top boss? So he's the ultimate parent. This 6 ultimate parent is connected. It will to the last 0. This again. So the height increased and the height one is up 3 times. So thereby we keep the same height. Perfect. Next, connect 4 and 5. Who is the ultimate parent of 4? Is connected. Height increase. Connect 0. So what you'll do is you will connect 7 and 6. So perfect. So who is the ultimate parent of 5? Let's see. Ultimate parent of 5. 5 is here. So 5's parent is 4. Who is actually the top boss? Who is actually the top boss? So he's the ultimate parent. Now I've been asked to connect 6. So 6's parent is 6. 6's parent is 6 himself. So ultimate parent is 6. Let's write the rank. Rank of 4, if you see, is 1. Rank of 6, if you see, is 1. Do you agree? You do agree. So apparently, I can say that, okay, fine. We have someone of the same ranks. So either this can go and get attached here, or either this can go and attach here. So you can do as you wish. So what I'll do is, I will just go ahead and take the 6 and make it attached to to 4. Done. And now I'll omit this. Remember one thing. You attached 6 to 4. So the parent of 6 will be 4. The parent of 6 will be 4. Remember this very, very well. Okay. Next, what is the other thing that you will do? You will have to increase the rank. Why? Because you had 4, 5. You had 6, 7. Both of the ranks, if you carefully see 4 and 6, had a rank 1. So since you attached same guys, height will, if you see the height increased, so apparently you go ahead and say the rank to increase by 1 more. So the rank will be 2. So this is where we stand till we have not performed the last step. Now, you've kind of understood everything. Now, suddenly if someone comes up and says, does 1 and 7 or do 1 and 7 belong to same compo? If I ask you this question, the answer is no. But how will you find out? This is where something like find parent will help. This is where something like find parent will come into picture. Okay, so since I'm saying find parent will come into picture, let's understand. So when I'm saying does 1 and 7 belong to the same component, I look at the parent of 1, it's 1. I look at the parent of 7, it is 6. So I'll be like, okay, the parents are different, they're not. But wait, you should not do like this. Just imagine you were having an 8 here. Imagine. Right? I'll ask, does 8 and 7 belong to the same component? Now something to notice, we are not creating a graph. We are creating a different data structure over here. A graph is not being created. Okay, a different data structure is being created. If I ask you if 8 and 7 belong to the same component, ideally they should. But if you will look at the parent, then 8 would have stored 5, 7 would have stored 6. Both have different parents. Can you actually tell on the basis of parents? Or do you need the ultimate parent, the top guy, the boss? You need the boss, you need the ultimate parent. So this is why, if I'm asking you who's the parent of 7, you say the parent of 7 is 4. So you go 7, you say 6. You see 6, you see 4. You see 4, you see 4. Oh, I'm the boss. That's why my parent is me. That's why you say the parent, ultimate parent. Boss is 4. And the boss for 1 is 1. So both have different ultimate parents. If both have different ultimate parents, you say they do not belong to the same component. This is the use of find parent. Now, since you're creating a kind of a tree structure, the tree will increase in depth with more number of edge additions. The tree will increase. So it will end up taking log n. It is theoretically proven. The tree will increase and it will end up taking logarithmic of n if you just apply union by rank. Because in order to find the parent of 7, you have to go from 7 to 6. From 6, you have to go to 4. And at 4, you find he is himself. So you get the top boss or the ultimate parent. That's going to take you a logarithmic of time. But wait, that's why you said it works in constant. It does. We apply something as path compression. Okay. So what I do is, I say, okay, someone did ask me to find the parent of 7. So what did I do? I went to 6 because 6 was his right father or the next parent. And 6's parent was 4. And 4 says, I'm the parent. So you can write something like this. Okay, I went from 7 to 6, 6 to 4. So I know the 4 is the parent. So once you have figured out 7's parent is 4, and since we are just dealing with parents and that is what I require, because our main goal is to figure out who is the ultimate parent. So can I say, once I've gone to 7 to 6 to 4, and once I figured out the parent of 7 is 4, can I actually say, I don't need this link anymore. Or I don't need this link anymore because I know 7's parent is now 4. So can I change 7's parent to 4? I can, because the next time if someone again comes up and says me, hey, does 2 and 7 belong to the same component? And you again go and call find parent, you will not move like 7, 6, 4. Because this time 7 will directly go to 4 and it will find him to be the boss. So you did a path compression. You did a path compression. You said, once I will just compress you. And then I know that, hey, listen, your parent is this guy. I know this. I don't need to go via 6. Imagine the tree to be longer. Imagine the tree was something like this. Just imagine. Take it as an imagination. Imagine the tree was something like this. And someone said, find parent of 5. So what will you ideally do? You'll go to 5, you'll go to 4, you'll go to 3, you'll go to 2, you'll go to 1. And at 1, you'll find he's the parent himself. And you'll say, 1 is the parent. You'll say, 1 is the parent. But what I will do is, I'll do a path compression. I know 1 is the parent. And 1 will be the parent of 2 also. So I'll say 2 is directly correct. 1 will be the ultimate parent of 3 as well. So I'll say 1 will be the ultimate parent of 4 as well. So I'll just remove this and say, and I know 5's ultimate parent will be 1. So apparently, a tree which was something like this, if you do path compression on finding parent of 5, 4, 3, 2, 1, and you get 2 as the parent, it returns 1, it returns 1, it returns 1, it returns 1, it returns 1. Because you went, and you backtrack to get 1, 1, 1. So what I'll do is, when this guy will return 1, I'll say, 3, your ultimate parent is 1. Why are you connected to 2? Why are you wasting your time getting connected to 2? 3 will be like, yes, does make sense. Let me connect to 1. 4 will be like, yes, I'm also wasting time. 5 will be like, I'm wasting time. Everyone goes and gets connected. So this is how the graph will change. Now, under 1, we will have 2, we will have 3, we will have 4, we will have 5 directly. Yes. So, this is for sure. And next time when someone comes up and says, find parent of 4, I'll be like, array, 1, direct, low, 1. Because 4 is connected to 1 and 1 is the ultimate parent. Someone comes up and says, find parent of 5, take 1. 1 is directly connected, ultimate parent. So this is what the path compression technique is. If someone is asking me parent, everyone in the path whom I encounter, I'll replace their links and attach it to the direct parent. But here comes a slight twist. I'll attach it to the direct parent, so it's fine. So what we usually do is, we attach it to the direct parent, and that's what we call as path compression. Okay? Remember this. So as of now, we have something like this. Now what will happen is, the next 3 and 7 will come. So I'll be like, you have to attach 3 and 7. So we know 3's ultimate parent is 1. And that's very easily found because 3 is directly attached to 1. But when I try to find out the 7, I'll have to find the parent of 7, which goes to 6, which goes to 4. And in order to find the parent, we will end up doing a path compression. So let's be honest, let's do the path compression, which will be something like this. And I'll find the ultimate parent of 7 to be 4, who is connected to himself, right? But if you do this, the tree will be something like this. And the rank of 4, if you carefully observe, is 2. But actually you have 5, 6, and 7. Ideally, the rank will also decrease, but we cannot do it. Because we're not sure of it. Because the rank cannot be reduced while path compression. The simple reason is, imagine you had something like this. And someone asked you to find parent of 8. So you went ahead and found parent of 8 and path compressed. So you reduced one section of the tree, but the other section is still having a bigger length. So the rank cannot be reduced. So that's why we call it as a rank and not height. If we can reduce it, we would have called it as a height. But since it cannot be reduced, we call it as a rank. Rank in the sense means this guy is bigger than this guy. Sorry, opposite. This guy is bigger than this guy. That's it. That's the meaning of rank. This guy is higher ranked than me. Got it? So the moment you find the parent of 7 to be 4, I find the rank to be 2, which means this is the bigger guy. So the smaller guy will this time come up and get attached to this guy. So what will happen is, this guy will come up and get attached to this one. So ultimately what we will have is, the parent of 7 will be 4, and I'll attach 1 to 4. So what will happen? The parent of 1 will now become 4, correct? So if I just draw it, it's going to look something like to this guy, correct? So will the rank change? No, it's still the larger guy. Attaching a smaller to the larger guy will not impact, because the rank of 1, if you remember, was 1. The rank of comes up and says, hey, does 3 and 6 belong to the same component? What you'll do? You'll call the find parent for 3, and it'll find you the parent to be ultimate. 3, 1, 1, 4, 4 himself. So again, a path compression will happen. Yes. When you find the parent, 3 will give you as 4. So the path compression will also happen. Find parent of 3 will give you 4. Find parent of 6 will be directly 4. So both of them have same parent or ultimate parent. So they belong to the same component. Quite easy. Since you're compressing the tree, the tree will be always of very limited size. In order to find parent, you have to do limited traversals. Always. Got it? So thereby the time complexity in order to perform the union operation is big O of 4 alpha. Now this 4 alpha has a huge mathematic derivation which is not required in interviews. You can say 4 alpha, which is as good as constant because the alpha's value is very, very close to 1. That is as good as a constant. And in order to find parent, it is also 4 alpha. So overall, the data structure works in big O of 4 alpha. Remember this, okay? So the question comes up, but Striver, how do we do path compression? You might be thinking, how do you do path compression? Because it looks scary because if you're connected to this, then you're connected to this, then you're connected to this, then you're connected to this, how do you path compress it? It's very simple. So 5's parent is 4, 4's parent is 3, 3's parent is 2, 2's parent is 1, and 1's parent is 1. So what you can do is you can backtrack. So you can write something as find parent and you can give the node u. Okay. And what will happen is you will say if u is equal to parent of u, then return this u. So basically, what does this mean? If at any moment 1 comes, 1 will be equal to parent of 1 because parent of 1 is himself. So I'll return the parent as 1. That's the base case because that is where you stop. Otherwise, you will be like, can you please return find parent of u? What does this mean? Imagine I give you 5. What will happen? It will go and say parent of 5. What's parent of 5? 4. It will go and say find parent of 4. So the next time find parent of 4 will happen. Does not obey. Again, it will say find parent of 4. Who's parent of 4? 3. So it will go on. So the recursion will be something like this. Function of 5 calls function of 4, calls function of 3, calls function of 2, calls function of 1. At 1, the base case is executed. And when it is executed, it returns 1. So this 2, which you would have called here, what you'll do is you'll say parent of u will be 2. So when it will return with 1, you'll say, hey, a 1, keep it, right? Keep it 1. Next, you will again return 1. You'll again return 1. So now 3 will also keep 1. Parent of 3 is 1. Next, you'll also return 1. So now parent of 4 will also be 1. Next, you'll also return 1. So parent of 5 is equal to 1. So everyone in term will assign 1 to it. If everyone assigns 1 to it, so automatically all the links will be path compressed and pointing to 1 and all these links will be destroyed. Rank and the path compression. Now it's time to code it up. So I'll try to create the data structure in a class so that going forward in the upcoming problems, we can use that snippet of code to solve almost all the problems. So we have a class of disjoint set. Nothing to worry, like don't get worried about a class. Very simple. It's a very simple thing. What's the initial configuration? Initial configuration required a rank and a parent. So just have it. And declare everything afterwards public. So all the functions can be reused outside. So now go ahead and declare the constructor. What is the construction? What is the constructor rather? So if you remember, I said you initially rank will be marked with zeros, parent will be marked with themselves. That is what we do. So we say rank dot resize of n plus 1 comma 0. Why n plus 1? Imagine it's a 1 based indexing graph. We need the nth index as well. If it's a 0 based, fine, but declaring it as n plus 1 will work for both 1 based as well as 0 based. Similarly, we can define parent dot resize of n plus 1 and we can keep it. And then we can go ahead from 0. Very, very important to go till n for 1 based indexing. And it'll be I itself. So this is how the constructor will look like. Now what does disjoint? And then we can go ahead from 0. Very, very important to go till n for 1 based indexing. And it'll be I itself. So this is how the constructor will look like. Now what does disjoint set give you? It gave you find ultimate parent, right? So this will be the node, and for this you have to find the ultimate parent. So we know one thing, if node is equal to the parent of node, this is the ultimate parent for sure. So you go ahead and return the node. But if it is not, then you call the ultimate parent and say go to its parent and then look for parent. But this is the normal logarithmic guy. We need the path compression. So this is where I can say whenever it returns the value, I'll store it so that in future if someone comes up and does ask me the same question, I can tell him that this is the parent. So this is where the path compression comes in. Path compression done. Next, what I'll do is I'll be like, okay, void union by rank is what I need to implement. Union by rank. So I'll have node u and node v, which I have to combine. So ultimate parent of, I can say ultimate ultimate parent of u will be find ultimate parent of u. Similarly, you can say ultimate parent of v will be find ultimate parent of v. Now I can say if ultimate of u is equal to ultimate of v, I can simply return. What does this mean? If they're belonging to the same component, I don't need, right? But if they're not belonging to the same component, I go ahead and the first thing I do is I check if the guy u is smaller than the guy v, right? So if v is the greater guy, the smaller goes and gets attached to the greater guy. So the smaller will now say, okay, I'll go and have the parent as v. No change in rank, because if a smaller guy gets attached to the larger one, there will be will now say, okay, I'll go and have the parent as v. No change in rank, because if a smaller guy gets attached to the larger one, there will be no increase, or that still stays the larger, right? Next, else if lesser guy, opposite. I say parent of rank, attach v to u, attaching it to ultimate of u will increase because that is where I am attaching it to. Ultimate of u will increase because that is where I am attaching it to. V attached to u, so the larger one will grow in size. So this is what I'll do. Once I've done this, I can say the union is done. This is how our data structure will look like. How can we use this snippet of code? So I'll just hard code it to show you how can we use it. It's pretty simple. So you can be like disjoint set ds. Whatever is the number of nodes. So in our case, it was 1. So I can have it as disjoint set of 7. So it will call this constructor and have the initial configuration ready for us. Next will be, I'll call it union by rank. And the first thing was 1, 2, if you remember in our example, right? So we'll have it 1, 2, 4, 5. Let's add the next was 3, 4, 3 to 7. If you do, and I will not, okay, so like, do you have the same boss? Not sim, right? Check answer. So I'll just go and compile this. So on compiling, it is saying, no, they do not belong to the same. And if I go ahead and move it to the next guy, it will actually say that they belong to the same. See, first time it says not same. Then on combining, it says same. So this is how you can always use the data structure. If you want to have 2 disjoint set data structure, you can go as DS1. You can have 2 different objects of this class, and you can have 2